Assalamualaikum and welcome to Prof. Sani. I am Daniyah binti Abdul Qadir with metric number BS201100004. Me and my group member Nurfatihah binti Ahmad will present about steel cross-coupling reaction. And I'm going to present about the part introduction, definition, methodology, and the advantages and disadvantages about steel cross-coupling reaction. Now let's begin. Welcome to the world of steel cross-coupling reaction, a powerful method for forming carbon-carbon bonds. Developed by Richard F. Steele in 1917. This reaction revolutionized in organic chemistry. This steel reaction involves coupling two organic groups. One of them is an organoidin compound, or known as organostenone, which is acting as nucleophile. With the presence of palladium catalyst, the organoidin compound reacts with organic electrophile, creating a new carbon-carbon bond. The steel reaction finds application in pharmaceuticals, agrochemicals, and material science, enabling efficient synthesis of complex organic molecules. Ongoing research focuses on catalysts, reaction conditions, and substrate scopes, enhancing the versatility and reliability of the steel cross-coupling reaction. Developed by Richard F. Steele, the steel cross-coupling reaction has had a profound impact on organic chemistry, facilitating the formation of carbon-carbon bonds and driving advancements in various scientific disciplines. Next, we're gonna explore about the steps involved in the steel cross-coupling reactions. The first step in the steel cross-coupling reaction is the preparation of organoidin compound, desynthesizing the desired organoidin reagent, which will serve the nucleophile in the coupling process. Second step is the preparation of organohalide, which act as the electrophile in the reaction. The organohalide can be a variety of compounds such as alkyl or aryl halides. Third step is reaction setup. Once the organoidin compound and the organohalide are ready, we set up the reaction. This typically involves the combining the two compounds in a suitable solvent, such as an organic solvent like tetrahydrofuran, or known as THF. Fourth step is addition of catalyst and base. To initiate the coupling reaction, we add a palladium catalyst, often in the form of a complex such as palladium chloride (PdCl2). Additionally, a base such as a triethylamine (ET3N) is included to facilitate the reaction. Next step is coupling reaction. With the catalyst and base in the reaction mixture, the steel reaction proceeds through the several key steps, such as oxidative addition, transmetallations, and reactive eliminations. These steps involve the formation of rearrangement of intermediates, ultimately leading to the formation of a new carbon-carbon bond between the organoidin and organohalide. And last is workup. After the coupling reaction is complete, we proceed with the workup. This typically involves the quenching the reaction with a suitable reagent such as water or an acid to deactivate the catalyst and remove any remaining impurities. The final product can then be isolated and purified using standard techniques. In a nutshell, starting with the preparation of the organoidin compound and organohalide, followed by the reaction setup, addition of catalyst and base, the coupling reaction itself, and finally, the workup to isolate the desired product. Advantages of steel cross-coupling reaction is toxicity and cost of organostenone reagents. Organostenone reagents used in the steel cross-coupling reaction can be toxic and expensive, which is required caution and proper handling. Second disadvantages is sensitivity to moisture and oxygen. The steel reaction is sensitive to moisture and oxygen, necessitating careful exclusion techniques to avoid side reaction or catalyst degradation. Third is limited functional group tolerance. Certain functional groups may limit the success of the steel reactions, required careful substrate selection and optimization. Not only that, the steel cross-coupling reaction also have its own advantages. First is various functional group compatibility. The silk reaction tolerates a wide range of functional groups, making it versatile for constructing complex organic molecules. Second is mild reaction conditions. The reaction operates under mild conditions, minimizing undesired byproducts and providing excellent control. And the last is broad substrate scope. The silk reaction can couple diverse organic molecules, allowing for the synthesis of complex compounds with diverse structural motifs. In summary, the steel cross-coupling reaction, despite its limitations, offers compatibility with various functional groups, mild reaction conditions, and a broad substrate scope, making it a valuable tool in organic synthesis. In summary, the steel cross-coupling reaction, despite its limitations, offers compatibility with various functional groups, mild reaction conditions, and a broad substrate scope, making it a valuable tool in organic synthesis. Thank you, that's all from me. Next, we're gonna move to my group member Fatihah binti Ahmad.
The steel cross-coupling reaction is the organic reaction of an organohalide with an organostane compound to give the coupled product using palladium catalyst. For the mechanism begins with the oxidative addition of the organohalide to the PDO to PD2 complex. The transmetallation with the organostane then follows, where the R group of the organostane reagent replaces the halide anion on the palladium complex. Reductive elimination then gives the final coupled product, regenerates the palladium catalyst, and the catalytic cycle can begin again. Moving on to examples of the product, the first one is polyfluorine, the second one is polythiophene, the third one is polypyrrole, and the last one is polyphenylene. I will be going to explain about the applications of the example of the products that I have been said before. The first one is the polyfluorine. Polyfluorine have emerged as a versatile semiconductor materials with application in various polymer optoelectronic devices such as light-emitting devices, lasers, solar cell, memories, file effect transistors, and sensors. The second one is polythiophene. Polythiophene are widely used in solar cells due to their ability to form better contact with metal electrodes. This polymer also used in polymer batteries and electrochromic devices. It can work with receptors for detecting metal ions or chiral molecules. Polythiophene shows potential in the treatment of prion diseases. The third one is the polypyrrole. This polypyrrole is a heterocyclic polymer that is both electrically and ionically active, and the polypyrrole has been investigated for sensing, drug delivery, and actuation due to its distinct characteristic. It has been utilized to interface the electrical elements and tissues, either for recording or stimulating purposes, due to its strong biocompatibility. Additionally, polypyrrole can be chemically altered to transport proteins and functional groups, so it can enable both precise biological identification and electrical stimulation. The last one of the application is polyphenylene. So, owing to its high temperature resistance, high tautness, good dimensional stability, and good rigidity, polyphenylene becomes an ideal material of choice in electronic and electrical market. Thanks to its exceptional dimensional stability, phenolphthalein can be used to manufacture heating and air conditioning components, fry pan handles, hair dry, and grills. Thank you, and that is all from me and also Daniyah. Thanks for watching our presentation video.